Okay, so today I am going to talk about polarization vector, electric susceptibility, and then I will try to find out the relationship between dielectric constant and electric susceptibility. So first of all, let us define a very important concept, that is the polarization vector. Polarization vector. So it is defined as the dipole moment per unit volume, moment per unit volume. So if p small p is the dipole moment of each atom, say it is the dipole moment of each atom, and let n be the number of dipoles per unit volume, then polarization vector, according to this definition, it can be written as small p multiplied by the number of atoms per unit volume. And let us try to look at the polarization vector in another way. So if we consider a small dielectric material and say its area of cross section is A, it is the area of cross section, and due to polarization, plus q charge will be developed on one face and minus q charge will be developed on the another face, and say dl be the length of this dipole, right? So now let small p be the this is another way to look at it. Say small p be the dipole moment due to induced charges right. This is the dipole moment because of this charge is induced here, and dl be the, then this small p, it can be written as qdl. Then, or in simply, let me represent this p as qdl. This is another way to look at it, right? So now, according to definition, dipole polarization vector is the dipole moment per unit volume. So volume is dV. Say this is the very small volume dV. So this p can be written as qdl, and this volume is area of cross section multiplied by length of this volume element. So this dl will cancel out, so it is q over a we are getting, and this is charge per unit area. So charge per unit area is nothing but it is the charge density due to polarization, right? Or the charge density of the induced due to polarization of the dielectric. So that means polarization vector can also be written as this one, right? So thus polarization vector may be defined as surface charge density of induced surface charge density induced due to polarization of the dielectric, or due to polarization in the dielectric, due to polarization of the dielectric. Right, so these are the two different ways to look at the polarization vector. One is this, another is this, and another way is this. These are the not two, but these are the three different ways to look at the polarization vector. Now let us talk about a very interesting concept that is known as electric susceptibility. Electric susceptibility. The polarization of a dielectric, as we know that polarization of dielectric is caused by electric field. So let us have a look at it, that how or what is the meaning of it. Say there is a dielectric material and it is placed in the electric field. Say E naught is the applied electric field. It is along this direction because positive charge will be on this and negative charge will over it, and because of this negative charge will induced over this surface and positive charge will be induced. So due to this, polarization electric field will be developed, but in a field opposite to that of the applied direction, right? It is applied in this direction and polarized field will be along this direction. So that means there is a net field in this dielectric. That net field is, it is E naught minus EP. So right, that's what will happen. So as polarization field is caused by the electric field, applied electric field, and because of this, keeping this concept in mind, we can say that this electric susceptibility, so the polarization should depend upon the net electric field inside the dielectric. Electric field inside the dielectric. So thus we can say that polarization vector is proportional to net electric field, and here this P is equal to epsilon naught chi E. Here let us try to look at this proportionality constant and epsilon naught. And here this chi E is called electric susceptibility. Electric susceptibility, and where epsilon naught is included to make chi E dimensionless, and in SI units chi E is also dimensionless. It has no dimensions, right? Now we have to find out the relationship between this, what we call dielectric constant, and chi E. This dielectric constant is as you have defined in the capacitor section, that it is E over E, right? It is the dielectric constant which we know, and also we know that another thing which we have to keep in mind, this EP is equal to sigma p over epsilon naught. These are the two things which we have to keep in mind, right? So as we also know that this sigma p is also polarization vector, right? So therefore this EP can be written as sigma p over epsilon naught, which is equal to p over epsilon naught, right? But what is the value of this p? The value of p, which we have defined as as we know that E is equal to E naught minus P over epsilon naught, right? Or E minus EP, and if I put its value here, then it can be written as EP, and it can be written as this E naught minus this is EP is P over epsilon naught. This is its value which I have substituted here. So that means E is equal to E naught minus P over epsilon naught, but this P is basically minus epsilon naught chi E over epsilon. This is the value of P, because P is equal to epsilon naught chi E. This we have defined during the definition of chi E, or the electric susceptibility, right? So this is E and this is E. If we bring these two together, then it is E plus epsilon naught chi E over epsilon naught, and E, this epsilon naught will cancel out with it is equal to E naught. And if we take E outside, then 1 plus chi E is equal to E naught, and 1 plus chi E is equal to E naught over E. So this is the dielectric constant. So this is the relationship between dielectric constant and electric susceptibility. Right, so this is all about this lecture. So this is a very simple and beautiful derivation for this, and this is a very important from the examination point of view. So that's all for